Right, let's get started. So today we are going to see the convolutional network, or just called the CNN, which is the extended version of the neural network that we discussed so far. So this convolutional neural network is it's a real starting point of the modern deep neural network. Anyway, let's go back to the image classification problem. Okay, so last week we discussed how to design your neural network and how to solve, how to train your neural network, because the neural network has a big capability to learn the complex mapping function like image classification, right? So in image classification, we have images, right? So our image, let's say xn is just an input vector, and our mapping function, let's say fwxn, will generate the output yn if we just consider a cat or non-cat problem. Let's say the binary classification problem. Yn is the binary output. Anyway, so fwxn may be formulated in a neural network, within a neural network. So yeah, so let's suppose like this. Let's suppose that xn consisting of the pixel, let's say 1000 by 1000 by 3, and each pixel value, I mean the x1 or x2, when I stretch the input images to the 1D vector, let's say like this is going to be the output for the MLP. Then the subsequent deep neural network can encode the feature vector with the learner parameter W and B. 그렇죠? It was a MLP or a neural network. But let's talk about dimensional learning of this problem. Great. Okay, so in this case, our images has some size 1000 by 1000 by 3. Then our feature vector, I mean the stretched feature vector, is going to be the 3 million. 그쵸? 3 million 맞나? 3 million. 3 그쵸? 3 million, just 3 million. Then let's suppose that you have a multiple hidden layer, but let's suppose that even for the first hidden layer, if you have a 100 node at first hidden layer, then your first MLP should be like this. So W should be in are 3 million by 100, even for the first hidden layer. So to design deep neural network, you're going to have a few more layers. That number of parameter in the neural network can be maybe infinity, almost infinity. Even though your how to say GPU or TPU has a good capability to handle the large scale data set or complexity, but this kind of complexity is going to be really huge, right? So that's the problem. That's the bottleneck when we apply the neural network to solve the high dimensional input or larger input. So how to handle this one? Local processing of data. Because the MLP, I mean the pure neural network or the MLP, just handle the image or the input as a whole. So that is the global processing of the data. So, but if we can locally process the data, let's say like this, okay? So let's suppose that you have images, but rather than considering this input image as a whole, by considering each local window independently, we can drastically reduce the number of parameters. Or let's suppose that you have a 1D signal like audio signal in this case. If we can handle this audio signal as a local chunk of the data like this, we can dramatically reduce the number of parameters. That is the starting point of the local processing of data, convolutional neural network. Convolution means how to design such a local processing of data. That's it. This is just the starting point of the convolutional neural network. How to do that? We can consider two kinds of things. First one is the parameter sharing, where in a manner that a filter that's useful in one part of the signal is probably useful in another part of the signal, right? Again, the parameter sharing means we can handle each local region with the same parameter. In convolutional neural network with the same column. That's the one first property. The second property is that sparsity of the connection. In each layer, each of value depends only on small number of input, not a whole input. Let's say one hidden node output just related to this local region, another hidden node output related to another local region. So that's the design philosophy of the local processing of data. The convolutional neural network. Convolutional neural network has a bit of the history. So first start of the convolutional neural network was the neurocognitive in 1980. In this paper, they tried to encode the images, but they first proposed the local processing of the data with a shared column, and by stacking the layer, they increased the depth of the data. It was the neurocognitron. Another paper was RBM in 2006, which was designed to handle the images like this. They have the encoder and decoder. We'll talk about encoder and decoder architecture in later of our lecture. But in encoder and decoder architecture, they also use the convolutional architecture. But the real starting point of the modern deep neural network and the deep learning was the AlexNet, which is the pure convolutional neural network based architecture. It looks like this. In lecture 7, we'll talk about the detailed architecture of the AlexNet, but the AlexNet consists of the convolutional processing like this. And as we discussed so far already, the AlexNet in 2012 dramatically improved the performance comparing to the shallow network and started the modern deep learning revolution. Anyway, so this is AlexNet. Then let's go back to today's topic. What is convolution? Formally, convolutional net, ConvNet, or convolutional neural network is a sequence of layer, and every layer of a convolutional network transform one volume activations to another through the differentiable function. ConvNet is a sequence of layers, and every layers of the ConvNet transform the one volume activation to another through the differentiable function. This is ConvNet. So every layer formally consists of three kinds of things: convolutional layer, pooling layer, or fully connected layer. Convolutional layer compute the output of the neurons that are connected local regions in the input, as we discuss here. We will see the details of the convolutional layer anyway. The convolutional layer compute the output of the neuron data connected to local region in the layer, and pooling layer perform a downsampling of the operation along the spatial dimension. We'll talk about this one later again. And fully connected layer is just the MLP that we discussed last week. Each neurons in this layer will connect it to the whole numbers of the previous volume. So this is a global processor. Neural network is just the pure neural network or the MLP. Let's say NN neural network. So today let's focus on the convolution layer. Okay. To understand the convolution or the convolutional layer, let's go back to the perceptron or the neural network. First of all, if you have the image, let's say 32 by 32 by 3, to process these images with a neural network, first of all, you have to stretch to this image to the 1D vector, let's say 3072 by stretching. Stretching. Then you're going to have the 1D vector. 그렇죠? Then, if you want to process this one as a neural network, let's say W with parameter W, the weight of the parameter should be 10 by 3072 that we discussed in the previous example. Let's say W is has the the row vector W1 transpose W2 transpose blah 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 W10 transpose, and each W in let's say are 30,000 by 72. 그쵸? Anyway, this is the W parameter, runner parameter. If you just consider if our output is 10 by 1, I mean we want to generate the 10 hidden node, then your runner parameter is going to be the 10 by 3072. It has two kinds of problem. So first of all, so by the way, so this each one number, so each number one number is the result of taking a dot product between the row of W. In this case, this one, 그쵸? W1, W2, W or Wn, and input, 그쵸? Input vector. Let's say 3000 by 3072. I mean, if we suppose that this is xn, then this one number, it's going to be W1 transpose times xn. 그쵸? Like this. He has two kinds of problem. First one is that if we stretching the 2D images to the 1D vector is not suitable in considering the spatial context of the 2D images. As we can see in the lateral images, the spatial structure have some kind of meaning. Let's say, okay, here is the face and here is the two eyes, or here is the two legs, something like this. 그쵸? Spatial structure have some kind of meaning, but if we stretch the input images as a 1D vector, we lose spatial context. 그쵸? Spatial context. This is first problem. Second problem, too many network parameters are required even for the images of a moderate size, like this. This is just a single layer, 그렇죠? But if we increase the hidden layer, if we increase the number of layers, our normal parameter is going to be really huge, as you can see here, 그렇죠? That's the problem. Then, how can we solve this one? How can we solve these two kinds of problems? That's the starting point of the convolution layer. Idea is very simple. If you want to consider the image, let's say 32 by 32 by 3 images, we want to preserve the spatial structure, right? Then your operator also, also have some dimensionality. Okay, so if you consider the image, you have a three axis, right? X-axis, Y-axis, or Z-axis, right? Then, if you want to preserve the spatial structure, you can design your filter or the learnable parameter has a 5 by 5 by, for example, 5 by 5 by 3 that preserve the axis X, Y, and G. So, then we can preserve spatial structure. Furthermore, if we just compute the one output by by dot product between this one. Okay, let's say that this is xn is the whole images and xn prime is the extracted patches within the image, let's say local patches. Then if we just assume that this is a w, I mean the learner parameter w, then we can generate the one output by multiplying wn prime and xn prime and w, then generate the one single output. In other words, from now on, we can just consider the local process rather than global process, right? To generate the one single images, one single hidden node. Then by considering the another local region, let's say here, then combo with the same kernel, then we can generate another output, right? Then by considering the whole possible patches within the input images, then we can generate the next, output with this learnable parameter. So this is the convolution. By doing this, we can preserve the special structure to solve the first case, and we can theoretically reduce the learnable parameter, because in this case our number of learnable parameter is 5 by 5 by 3 compared to this one. This is very, very small number of the parameter. So this kind of process is called the convolution. So it means that we convolve the filter, let's say filter, with the images that is slide over the images spatially, comparing the dot product like this. This is convolution layer. That's it. That's very, very simple, right? So one more thing is that in image process, the computer vision, convolution layer mention 2D convolution layer. Of course, there are higher dimensional convolution, let's say 3D, 4D, something like this. But in general, we will talk about the 2D convolution layer. In the case, filters always extend to the full depth of the input volume. What does it mean? If we just consider the 32 by 32 by 3 images, and then your kernel should have the same depth of the input volume. In this case, 3. So your kernel should be 5 by 5 by 3. Even though 5 by 5 can be varied, this 5 by 5 is the hyperparameter that we have to tune. But the number of filter, the number of depth should be same to the input of this single convolution layer. That's it. To sum up, in convolution layer, 32 by 32 by 3 images, let's say X, then X prime means these local images, then with one filter, let's say 5 by 5 by 3 filter, or often called kernel, we can generate a single output, right? Let's say Y. So in other words, the result of taking the dot product between the filter and small 5 by 5 by 3 chunk of the images, let's say X prime, then this Y is equal to W. In this case, W 5 by 5 by 3 times x prime plus bias. So we'll talk about how to compute the dot product between the 5 by 5 by 3 time 5 by 5 by 3 tensor by 5 by 5 by 3 tensor. But one very simple method is just the least side. So as a 1D vector, it's going to be the 75 dimensional vector dot product and with a single bias term, similar to the neural network. So that's it. So that generates one number. One number. Then by combo or slide over whole special location, let's say first one is here, second is here, third one is here, blah blah blah. By comboing this one, we can generate image like output. Each value determine. Determine each hidden node. That's the convolution layer. This is one convolution layer. In other words, if your input images has 32 by 32 by 3 number of I'd say the element, and your kernel was 5 by 5 by 3, by combo or by comboing or the sliding over whole special location, you are going to generate the new output whose size was 28 by 28. Why 28 by 28? You can easily think like that. So here is the 5 by 5, right? And by considering the whole possible patches, here is another 5 by 5, right? So then, naturally, the output is reduced from the 32 to the 28. And anyway, this is the output of the convolution, one convolution layer, with the parameter 5 by 5 by 3 filter. So in convolution layer, this output is often called activation map. Activation map. It's not an activation function. It's activation map. Activation function was like the segment function or this, but this map is also called the activation map. That's the definition. There is no specification, though that's the definition. So please remember that. Anyway, this is activation map. Okay. So anyway, the output in this case, output is let's say y in 28 by 28 by 1. 28 by 28 by 1. 28 by 28 by 28 by 1. With learner parameter 5 by 5 by 3. 5 by 5 by 3. But the reason we use the neural network is to increase the model complexity, right? While reduce the learnable parameter reasonable manner. So another very interesting idea. Consider the second or green filter or another filter. This is the first filter. Let's say 5 by 5 3 filters, and let's talk about another filter, 5 by 5 by 3 filter. Then you can generate another activation map with size of 28 by 28 by 3, right? By doing this, for example, if we had 6 5 by 5 filter, 5 by 5 by 3, but 3 is just predefined because it depends on the input, 그쵸? Input size. Anyway, if we had 6 5 by 5 by 3 filters, we will get 6 separate activation map. Let's say 1, 2, 3, 4, 5, 6, 1, 2, 3, 5, 6, right? Then your output y in 28 by 28 by 6, 28 by 28 by 6. If your input was in 32 by 32 by 3 with convolution layer with parameter 6 kinds of 5 by 5 by 3, right? So let's say five by 5 by 3, and there are 6 different kinds of parameter. 5 by 5 by 3. There are 6 kinds of things. 그렇죠? That's the learnable parameter in convolutional layer. Anyway, this convolution layer is another mapping function fwxn, right? Fwx, right? Then this w has some 2 parameter. Just w parameter that we discussed here. So this is w, and one more thing was the bias. 그쵸? Bias. In this case, bias was just what else? Bias is just a 6 value. 그쵸? 6 value. I mean the 6 by 1. 그쵸? Because we consider the 6 kinds of kernel, so the number of bias is the 6 by 1. 6 by 1. This that's similar to the neural network. Anyway, we stack this up to get new images or the new activation map of site 28 by 28 by 6. That's the one convolution layer process. So, one convolution neural layer process. In other words, we can generalize like that. You have an input of size h1 by w1 by c1. C1 is the channel, right? Then you want to generate the output of size h2 by w by c2 with convolution layer. Then the weight, I mean the w of the convolutional layer have the C2 should be the output channel. Filters of the FH times FW times the C1. C1 is the the channels of the input. Channels of input. Then, in other words, this convolution layer has the number of weight C2 times C1 times FH times FW, and additionally has bias. The number of bias was C2. This is the same as the number of filter. In this case, C2. Anyway, this is the learnable parameter in the one convolution layer. In this case, W and B. Then we can generate output of size H2 by W by W2 by C2. 그렇죠? 자, 여기까지. 그래서 뭐 한국말로 한 번 정리하면 뭐 어렵지 않죠. 그래서 쭉쭉 가보면 컨볼루션이라고 하는 게 왜 나왔느냐라고 생각하면 결국에 아까 MLP로 이제 우리가 프로세싱 하려고 보니까 사실 거의 불가능하죠. 이미지라고 하는 데이터를 하는 건 불가능하고 그 러너 파라미터 너무 많기 때문이에요. 그렇기 때문에 너무 많은 넘버 파라미터, 러너 파라미터가 필요하고 일단 이미지라고 하는 것 자체는 어떤 스트럭처, 스페셜 컨텍스트가 중요한데 그게 다 깨져버리는 거죠. 스트레치를 그러니까 원디벡터로 만드는 순간. 그렇기 때문에 이렇게 커널을 5x 5x 3, 즉 이미지의 스트럭처를 보존하는 커널 사이즈를 만들어서 로컬 프로세싱 해보자 라는 게 바로 컨볼루션의 아이디어였고요. 그래서 이런 식으로 설계를 하죠. 그래서 이제 인풋에 나올 수 있는 chunk of the data와 쭉 프로세싱을 해보면 이제 우리가 열심히 이렇게 하면 이런 식으로 슬라이딩을 돌면 이제 이런 사이즈 아웃풋을 만들어낼 수 있고 이게 이제 하나하나가 다 히든 노드 값인 거죠. 그쵸? 그래서 이제 이거를 우리가 필터의 개수를 여러 개 해보면 이걸 이제는 이 뎁스를 낼 수가 있게 되고 그래서 인 제너럴하게 C2개의 필터를 고려를 하면 우리 아웃풋은 H2 by W2 by C2가 되더라. 그쵸? if input이 H1 by W1 by C1이고 필터, 사이즈 오브 필터가 FH by FW by C1인 경우에 이제 이렇게 되더라. 그래서 이제 이 하나의 레이어, 결국 어쨌든 이게 우리가 펑션이라는 개념을 표현했어요. 그쵸? 그래서 어쨌든 이것도 하나의 펑션. 그쵸? 결국에 이 number of parameter 펑션 넘버 파라미터 결국 W와 B였을 텐데 여기서의 B는 W와 B가 이런 식으로 설계되더라. 즉 결국에 여기서 우리가 알아야 되는 이 C2, FH, FW가 결국에 하이퍼 파라미터더라. 그쵸? 우리가 어떻게 정의하에 따라서 달라지는 거고 이 사이즈 안에 들어가는 파라미터들이 옵티마이즈가 되는 거죠. 러닝이 되는 거죠. 그쵸? During the training time. 그쵸? That's the convolution layer. Okay? Okay. So, convolution is a sequence of the convolution layer. Is first with nonlinear activation function like a ReLU function, 그렇죠? But convolution anyway, sequence of the convolution layer. It means that from now on, we will use the several kinds of the convolution layer by stacking convolution layer like a deep neural network. Let's say here's the one convolution layer. Here's another convolution layer, and here's another one more convolution layer, right? By stacking this convolution layer, we are going to say this is the deep convolutional. Deep convolutional layers or the neural network or just net, deconvolution or deconvolution. That's the starting point of our lesson, right? Let's talk about dimensionality. For example, your input images has size of 32 by 32 by 3. Then if your first filter was 5 by 5 by 3 and you have a 6 different kinds of filters in this case. Anyway, your just one filter just generate the one value. Then by convolving this one, you are going to generate the 28 by 20 by 6 that we discussed here. 그렇죠? Here. Then this one is going to be the another input for this next convolution layer. Then let's suppose that your convolutional kernel was 5 by 5 by 6 and you have a 10 kinds of output, 10 kinds of kernel, then your size is going to be 24 by 24 by what? 10. 그렇죠? It is related to the number of filter of the convolution. Then this 6 is related to this one and this one. 그렇죠? That we discussed. And we can process the data furthermore with another convolution layer. Then we can increase the depth of our network. That is convolution, which is a sequence of the convolution layer. That's it. So anyway, this is a visualization of the trained kernel. The trained CNN kernel. So for the second project, we will see. We will solve the. We will implement this convolutional neural network, deconvolutional network. But this is one of the example. Let's suppose that this is images. Word activation because the input image also activation. Let's say 32 by 32 by 3 because this is a color images. 그쵸? 32 by 32 by 3. Let's say this is xn. And if we consider 32 by 32 different types of 5 by 5 by 3 filter, let's say this is also one filter 5 by 5 by 5 by 3 because this is a color. That's each filter has a color information, and this is a Lund picture vector. The Lund kernel. Let's say this is here are 32 kinds of things, 그렇죠? Because we just assume that we have a 32 times 5 by 5 by 3 kernel. In other words, our W, Lund parameter, in 32 times 5 by 5 by times 3. And 3. Anyway, this is the learned filters, and this one single filter generate one activation map by combo with these images. Then generate the one activation map. Then activation map, size of activation map, I mean the one slice of activation map is 28 by 28 by 1 that we discussed previously. 그쵸? Then combo with a different filter, we can generate a different activation map like this. When you consider this one, then given these input images, we can generate this kinds of activation map or activation images. Interestingly, different filter can extract the different kinds of the feature property given the input image. That's the beauty of the the convolution layer. I mean in convolution neural network, we can extract the deep understanding of the input images. Let's say, okay, in this filter vector, we extract this this shape, and this filter vector, this filter extract this light information or so on. Then we can comprehensively understand your images or input. That's the convolutional network. Anyway, the output of this one convolution layer was like 28 by 32. 그쵸? Then one slice of this picture, I mean the output activation map. Which one? This one. 그쵸? 이렇게 변될 수 있더라. That's the visualization of the convolution. 그쵸? Why we call these kinds of things as a convolution? We call the layer convolutional because it is related to the convolution of two signal like this. When we consider the define of the convolution f combo the g, then the equation is like this. 그쵸? f combo to g. Elementize multiplication sum of the filter of the signal. This kind of process is exactly same to this process, so that's why we call this process as a convolution. 그쵸? So this is the visualization of convolution. Okay. So anyway, to understand the convolution further, we have to discuss the recessive field. 그쵸? Recessive field. What does it mean? Let's suppose that this is input images. Input images, and we have a two convolution layer. Let's say here is a combo 1 with 5 by 5 by 1 filter. Here's another combo 2 with 5 by 5 by 1 another filter. Then input images processed with so this single value processed with this 5 by 5 shape, right? Then each values can relate it to this one or this one or this one, right? Then after convolution 1, when we consider the convolution 2, this one output of the one convolution 2 related to this one. In this case, a 5 by 5. So this single layer was 5 by 5, right? Then by considering each output related pixels, I mean the related input element for this single node, it's going to be the 9 by 9. 9 by 9. 그렇죠? By just considering the shape of the rectangle. 그렇죠? 아니 square. 그렇죠? Anyway, in this case, to extract this one vector, the one value, input 9 by 9 input effect on this one output and the one output. So in other words, recessive field or the effect of recessive field with this component, which has consists from the combo 1 and combo 2, is 9 by 9. 9 by 9. Because of 5 plus 5 plus minus 1. Why minus 1? Just try to do in yourself. 그렇죠? That's the very straightforward. The 아무튼 straightforward, right? Another perspective is from the convolution property. Convolution property. If this one is y and x convolve to h1 and z is y convolve h2, then z is x convolve h1 convolve h2 convolve, then x is going to be the x convolve h. Then h is h1 times h2. That's it. So the size of the reset field, the reset field is the size of the input image that effect on the one single output given the this convolution layer. That's the reset field. So in other words, if you consider the convolution layer, you have to answer what is your reset field given this convolution network. 그렇죠? That's the reset field. 그래서 뭐예요? 우리가 하나의 싱글 아웃풋을 내기 위해서 인풋이 어느 정도로 영향을 미쳤느냐를 사실 알아야겠죠. 그렇죠? 그래서 이걸 하나 내기 위해서는 요만큼 9x9 영향을 미쳤겠죠, 사실. 언제? 우리가 컴플 레이어가 두 개인데 5x5x1 필터 두 개인 경우에, 그런 경우에 우리가 9x9 영향을 미쳤다라고 할 수 있는 거고, 이제 그게 바로 이제 리셋 필드라고 하는 개념이에요. 알겠죠? 리셋 필드라고 하는 개념이더라 라는 얘기죠. Anyway, so by design, convolution in a hierarchical manner, let's say combo 1 and combo 2 and combo 3, we can extract the feature vector and the sequence picture vector. Let's say x. Okay, let's suppose that this is x and this is the the first output, second output, let's say third output. Then the learned filter has a different property. This is activation map. Let's say like this, or we can just say this is a feature or activation map. Okay, let's say activation map or filter or the feature. Then by stacking this convolution, we found that here there are hierarchy current information. For example, okay, so we can just say that this is a low level, middle level, and high level. Then when we visualize this activation map, let's say this one and this one and this one, it encode. This is the visualization of kernel itself. This is actually kernel itself, and or activation map. This is activation map given this one. Anyway, we can find that very interesting observation. So low-level feature vector just encode the low-level structure like edges or the color, and if we increase the level of the feature, the second level, it extract some kinds of middle-level feature like a circle or the set of the line, right? Then by encouraging the hierarchy, by considering the next level, we can extract the more higher, high level information. Let's say the the face of the face of the I don't know exactly, but something like this. Face of what, or the other semantic structures, something like this. So we can just found that. We can just say that semantic hierarchy from images. That's a very, very important finding. Why? So when AlexNet was first developed, there is no explanation. There's no way to say to argue the reason. Why such a component, the sequence of the convolutional layer can give the better performance. But after that, we just visualize this learned corners or the activation map. This is the learned parameter trained on ImageNet, 그쵸? AlexNet trained on ImageNet. Then we just found that convolutional component itself has some hierarchy, semantic hierarchy, similar to us. As human being, right? So that's the key component of the succeed of the convolution layer. So by doing based on thanks to this good property of the convolution layer, we can achieve the better performance. That's a very important thing. Anyway, this was the hierarchy of the convolution layer. Okay, and of course, convolution layer or the other team learning network is just a black box. Even though this is even though there are some recent work to visualize the neural network, but it's just a black box because there are so many kinds of number of parameters, right? But fortunately, if your model is very small, like I'll say the digit recognition, you can just see the learned parameter. For example, like this website. So it's very interesting. So please try to do this, to see the learned parameter and to see the the relationship between the first layer, second layer, third layer, so on. That's the convolutional neural network. Anyway, let's closer look at the spatial dimension. We already talked about this one. Okay, so let's talk about you have a 7x7 input, or you have a channel. Then you are going to be the channel, but we are just interested in the spatial dimension, right? Why? Because the channel, normal channel should be same, 그렇죠? So we're just interested in the the spatial dimension. Let's say input was a 7x7 and filter is 3x3. Then what is the output? For example, if we consider 3x3, this 3x3 will generate the one output. Or the 3x3, the 3x3 with a different window can generate another value. By considering the whole, the spatial window, we are going to generate 5x5, right? If your input was 7x7 and filter 3x3, your output is 5x5. That's the definition, 그렇죠? That's the definition here. In some case, we may require the stride concept. What does it mean? Stride mean, okay, even though we consider the same kernel 3x3, like this, and extract the one value, right? Rather than consider this one, but also skip this this window and consider this window directly, then generate another vector. This is kind of stride concept. This one, stride. Why do we have to consider the stride? Why? Just to reduce the output. That's it. In this case, your output is going to be a 3x3. Even though if there is no stride, the output was a 5x5, but with the stride, we can reduce a 3x3. So that's the way to reduce the memory. In this case, the output. Then this output is going to be another input for another convolution layer that eventually we reduce the number of parameters. So that's the that's the concept of the stride. Then let's formulate. Let's make a very powerful relationship between the size of input, size of filters, and stride. Then your output is going to be n minus f divide S plus 1. That's the output side. Of course, this is just the single axis output. 그쵸? 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 So, for example, if your input 7 by 7, 7, 3, 그쵸? 2인 경우는 어떻게 돼요? For example, 7, 3, 2 plus 1, 그쵸? 인 경우는 4, 3, 3. So, was 3 by 3. That's it. That's the equation about spatial dimension between the input and output of convolutional neural network. Please do not ask why. You can just do that. Just this is just definition. Why? Because here is the n by n, and your size is 7 by 7, f5f, and you going to consider the stride. Then your output side should be like this. That's the definition. One more thing is the padding. What does it mean? Right? If you just consider the images directly, for example, if you consider the 3 by 3 column, your output starting from here, start to here. But in some cases, you may want to handle, you may want to, process even this one, 그쵸? Even this pixel. But there's no values, 그쵸? Initial, right? So, in many cases, we just pad, zero pad the border. Let's say zero pad or zero padding. How? Just assume there is the zero value. 그쵸? Then process data. Then your first window start from here. 그쵸? From here. Then maybe your output is going to be a little bit large, but we can estimate the value for this pixel as well. That's there is some kind of application that requires even process the boundary information. Anyway, so in this case, n by n input, f5f filter applied with stride S, path with a p pixel, then output is going to be n plus 2p minus f over s plus 1. Please don't ask why. Don't ask me why. Do it yourself. Okay? That's very, very intuitive way. Just a hint. This is the n, 그쵸? And path means here is a p and here is p. Then we just assume that here is the very large another images whose size was n plus 2p. Then it's going to be exactly the same to this equation. 그쵸? Anyway, please do it yourself. 그쵸? Anyway, with this equation, we can easily say the output size given input, filter, stride and path. So, number of column, the size of column, stride, path, or padding, is just a hyperparameter. That we have to tune. Just for the one single convolution, right? So if you consider so many kinds of convolution layer, let's say the 100 or 200, you have to consider the very big number of the hyperparameter. Anyway, if you just assume like that, then your output side is going to be 7 plus 2 times 1 minus 3 over 1 plus 1. So it's going to be the 7. It means that your next input is going to be the 7 by 7. Given input was the 7 by 7. So by doing this, we preserve the data and we preserve the resolution. 그렇죠? From 7 to 7. How? By just considering the path. Right? some application requires to like that, something like that. 그렇죠? Some require doesn't want reduce, I mean the lose some special dimensionally. So that's the one example. 그렇죠? That's it. To sum up, we can summarize the special dimension of the commotion layer. Like this. Let's suppose that your size of commotion layer was the W1 times H1 times T1. Then with one component, let's say comp 1. Let's suppose that your output size was W2 times H2 and D2. Then your size of the kernel was T2 times F times T1. Like this. 그래서 the accept the volume size, I mean the input size was the W1 by H1 by D1. But maybe you want to write the size of the input as H1 by W1 by T1, or you may prefer to use D1 times H1 times W1. That's whole fine. I mean that's exactly same. I mean if we consider this like tensor by changing the axis, we can just write that. But the one thing is that we have to just we just fix the rule to write the dimension. I mean if you want to start the x-axis first, you can just write that. Then you always have to like that. 그렇죠? So that's very important thing. 아마 이제 이거 보다 보면 여러분들 질문하는 학생이 있는데, 교수님 H1, W1은 D1으로 쓰면 안 되나요? 또는 저희가 쓰는 라이브러리는 D1, H1, W1으로 하던데 다 돼요. 상관없어요. 결국에 제 항상 써보셔야 되겠지만 결국에 똑같은 단서를 우리가 쉐입만, 그러니까 뭐예요? 이렇게 디멘전만 돌리는 거죠, 사실. 그쵸? 결국에 아무 상관이 없고, 그 말은 뭐냐? 그 대신 우리가 정해진 걸로 똑같이 쓰면 돼요. 우리가 항상 W를 앞에 쓸 거면 W 앞에만 쓰는 것만 정해주면 상관이 없겠죠. 근데 이게 중간중에 바뀌면 완전 다르게 되겠죠. 그쵸? 그래서 이제 그거를 조금 고려해야만 돼요. Anyway, we have a full number of private parameters. So K, F, S, P. 그렇죠? K, F, S, P. Number of filter, special extension, stride, and padding. Then suppose that your output was W2, H2, D2. Then W2 and H2 size is going to look like this, as we discussed here. 그렇죠? Here. Then D2 is going to be the K. I mean the D2 is going to be the number of the filter. So we discussed in previous slide. 그렇죠? 의미를 알겠죠? With parameter sharing, it reduced the FFD1 weight per filter. So for total of FFD1K weight with K bias. 그렇죠? This is the learnable parameter. The output volume, this depth size of W2 times H2, 그렇죠? Like this, is the result of performing the basic commotion of the filter over the input volume with the stride S, then offset by this bias. 그렇죠? That's the definition of the convolution, right? It means that if you want to design the one commotion layer, you have to tune this hyperparameter. How to tune? How to tune this parameter? Model selection again. That we discussed previous lecture. That's another problem. 그렇죠? Of course, there are some, I'll say, guidelines to make a better neural convolutional network, but there's no rules. There's no golden hyperparameter, rule them all. So we have to find out optimal hyperparameter with like a model selection. 그렇죠? 어쨌든 이게 우리가 항상 얘기했죠. 컨볼루션 레이어도 어차피 하나의 펑션에 불과하다. 결국 그 펑션에 들어간 하이퍼파라미터 우리가 튜닝을 해야 된다라고 하는 얘기죠. 그렇죠? 그렇죠? 다 이해했죠? Right. So this is a makeup class for this Wednesday. So I think that's it. So if you have any question, because this is just a recorded video, if you have a question, please send me an email. Then I will let you know. I will reply as soon as possible. Then, right. So thank you very much. That's it. So yeah. Thank you for listening and see you next Monday. 자, 이제 여러분이 오늘 이번 주 이제 우리 월요일 그 메이크업 클래스였고요. 이번 주 월요일이 언제였나? 10일이었죠? 10일에 메이크업 클래스였고 이제 이거 듣고 꼭 여러분 우리 월요일 수업 시간까지 듣고 월요일 수업 시간에 이제 컨볼루셔널 레이어 이 챕터 마무리해 봅시다. 알겠죠? 여러분 프로젝트 1 나간 거 잊지 마시고 질문 있으면 저한테 메일 보내주시고요. 우리는 다음 시간에 보겠습니다. 여러분 수고하셨습니다.